I am super, super excited to have as our first keynote speaker of our CAGLA conference, Mr. Walter Isaacson. Mr. Walter Isaacson is a graduate of Newman High School. He went on to Harvard. Then he was a Rhodes Scholar at Oxford. And from there, he moved on and became ultimately president and CEO of CNN. He was editor of Time Magazine, president and CEO of Aspen Institute. But his real passion, from my understanding, is writing books. And I've read most of them. They're awesome. He's written the books on Henry Kissinger. He's written books on Ben Franklin. He was the handpicked person to do the authorized biography of the late Steve Jobs. He was recently picked by Elon Musk to write his authorized biography. But his most recent book is a book called The Codebreaker. It's about a medical scientist called Dr. Jennifer Doudna. And she recently, I think a year or two, won the Nobel Prize for gene editing. I don't know if people have heard about what CRISPR is, but you can Google it. So today he's going to talk about his latest and greatest book called The Codebreaker that chronicles the life of Dr. Doudna. So without further ado, ladies and gentlemen, please give us a warm welcome for Mr. Walter Isaacson.
Hey. Thank you. Thank you very much, Chad. And thanks for all you do, but everybody in this room, the cancer advocacy groups like this, especially Cancer Advocacy of Louisiana, my home state, is very important, and you're doing it at a crucial time. As Chad mentioned, we're entering into an entire new innovation revolution, and it's going to impact medicine, the life sciences, and in particular, cancer. All the books I've written about are about great innovation revolutions. It starts with the idea of a scientific revolution with Galileo and Leonardo. Ben Franklin brings that notion of the experimental view of science to America, to governance, to checks and balances in our Constitution. And we see, extending from that, the ability of the scientific method and of innovation to change and create revolutions. In our time, there were really three great revolutions. By our time, I mean beginning in 1900. The first was the revolution based on the atom. All of these are based on fundamental particles of nature, but the first one is the one based on the atom. And it's a physics revolution that happens in the first half of the 20th century. It begins with Albert Einstein's three amazing papers in 1905, his miracle year, in which he does relativity, quantum theory, and then eventually has the most famous equation in all of physics by the end of 1905, which is E = mc squared. The physics revolution of the early 20th century, of the first half of the 20th century, Einstein's fingerprints are all over it, from space travel to the atom bomb to GPS to semiconductors. And we have a revolution that's based on these wonderful new ideas of what you can do with the fundamental particle of the atom and what you can do with physics. The second half of the 20th century was a digital revolution. And that comes from another fundamental particle, which we call the bit, which is simply a binary digit, a 0 and a 1. And the notion that all information, all pictures, all words, all music, all video, everything can be encoded in a digital format, and we can use circuits in order to manipulate it and send it around, creates a digital revolution that begins with the invention of the transistor, the microchip, the computer, and then the network, all separate inventions in the 1950s. But when they're brought together by the 1970s, we have this revolution that I'm not sure all of you were sort of noticing it, but it's a revolution of our lifetime, the revolution from 1950 to the year 2000. And then finally, we get to the new revolution, the one that starts in the year 2000 and will be for the next 50 years, the revolution we're in now. It also comes from a fundamental kernel of reality. The atom, the bit, and this fundamental kernel is the gene. The gene that passes along hereditary information or messes it up, and we end up having cancer. And instead of microchips with zeros and ones, we'll now have coding that involves the 4 letters of our genetic code. And molecules will become the new microchip. And that's what the code breaker is about. And it deals directly with cancer treatments and cancer care, as well as virus treatments, of course, as well as mRNA vaccines. And the person at the heart of this revolution is Jennifer Doudna. Now, I write biographies, and most of my biographies, I don't have to tell my editor when I say, here's what I want to do next. She doesn't say who, because I usually just say Einstein, Franklin, Jobs, Leonardo. But when I said Jennifer Doudna, she was actually quite thrilled. I thought she would say something like, wait a minute, a person with an unpronounceable name who discovered an acronym that nobody knows what it stands for. But she said, no, I get it. This is what the 21st century is all going to be about, which is this life sciences revolution. And Jennifer Doudna is a biochemist growing up in Hilo, Hawaii. Like most people I write about, she felt like a bit of an outsider. And you say, why? You know, a lanky, tall, blonde girl. But she grew up in a town of all Polynesians, and she was made to feel like an outsider. So she became a voracious reader. Her father used to bring her a book from the library or a used bookstore every week, and she'd read it every week. And one day, he left on her bed, that's the Signet paperback edition of probably the most interesting life sciences mystery story of the 20th century, James Watson's The Double Helix. As you know, Watson and Crick, along with Rosalind Franklin, whose data they used without her permission, end up discovering how DNA is structured and how it becomes the code that passes on the essence of every living thing on this planet. How it passes along the genes, how it passes along what life is all about. Jennifer said that when she first got it, she thought it was a mystery story because it looked kind of strange, the helix or whatever. And she put it aside till the rainy Saturday of that week, and she discovered in some ways it was a mystery story. It was about the greatest mystery of all, which is the code of life, and the hunt for it. How people decided to try to figure out what was this mystery. They used all sorts of experiments and ways to understand the essence of life itself, and that totally thrilled her. She said she also noticed, and if you've read the book, I'm sure most of you have, that Rosalind Franklin is, as you may have noticed, is treated rather dismissively by Jim Watson, who is he's the greatest scientist, biologist of the 20th century, but not the greatest human in some ways. He turns out to be quite strong in his politics, let me say. And it's also dismissive of the person he calls Rosie, even though Rosalind Franklin never called herself that. But despite that, Jennifer Doudna says, up until then, I never realized that a woman could be a scientist. She's about 14, 15. And everybody in her class, boys and girls, are supposed to be saying, what are you going to be when you grow up? And she tells her guidance counselor in the public high school in Hilo, Hawaii, that she wants to be a scientist. And he says, what a lot of male guidance counselors probably said back then, which is, oh no, girls don't generally do science. Well, this, of course, transformed Jennifer into somebody who decided that she was going to discover, and she was going to study the mechanisms of life. As she walked around Hawaii, she loved the sleeping grass. When you touched it, it folds up. All of us remember things like, touching a Venus flytrap or something, and it curls up. But really great creative people have a curiosity, and they just keep wondering, how does it do that? What codes it to say, you should open up for the sun, you should curl up when some other organism touches you? And so she becomes a chemist at Pomona College. And she makes another discovery that's happening around that time in the 1980s, which is that chemistry and biology should actually be one subject. And that if you're going to understand how the world works, you have to understand the relationship of chemistry to all of our biological processes. When I first was given this book by my father here in New Orleans, I still have the pale red hardback edition, which would probably be valuable. It was the first edition, but it has all my scribbles in the margin, messing it up. And the very first scribble was of words I didn't fully understand or was new to me. And the first word was biochemistry. It was a word I had never heard of, but it becomes the watchword of 21st century science. After Pomona, she becomes good at chemistry there. She tells her father that she's probably wants to study science more and is applying to the University of Hawaii. And her father says, well, why not Harvard? And she said, well, Dad, I'll never, from Pomona as a chemistry student, I'll never get into Harvard. And he says, you're right, you won't get in if you don't apply. So she applies, and of course, you can figure out the upshot of the story, which is she gets accepted to Harvard and gets to study under Jack Szostak. That's Jack Szostak, who taught her many things, one of which was the importance of DNA and its lesser-known sibling, RNA. Now, like a lot of famous siblings, DNA gets on the cover of magazines and everybody knows about it. Up until COVID, most people really didn't focus on RNA. But like the less famous sibling in any relationship, it's the RNA that actually does the work. As you know, DNA just sits there in the nucleus of our cells, curating information, never going anywhere, just sitting there curating the information, doesn't do anything. The RNA comes in and takes blueprint from that information, goes out into the protein building region of the cell, and builds a particular protein based on whatever instructions the DNA was hoarding in the nucleus. And Jack Szostak tells Jennifer Doudna, his graduate student, you always have to look for the big question. And she says, what's the big question here? And he says, how did life begin? And they start studying RNA that can replicate itself. Because one of the curious things about how life began is you can't have DNA creating new forms of life and replicating without proteins doing it with them. And it's a whole chicken and egg problem. But they discover that some forms of this molecule, RNA, that just has 4 chemicals in it, 4 bases, can replicate itself, copy itself, and thus can be the beginning of life. I think that might be Lake Pontchartrain and Lake Borgne 3 billion years ago. But that's 3 billion years ago. What they figure out is the RNA world, in which this primordial stew of chemicals existing on Earth jangled together, and at some point these 4 base pairs come together, form RNA, and the RNA starts replicating itself. And thus, we have the secret of the beginning of life on this planet, and also the importance of RNA, not just DNA. Jack Szostak wins the Nobel Prize for his discoveries on self-replicating RNA, but on the paper that he wrote, the graduate student, who's the main person credited as well, is Jennifer Doudna. Jennifer goes on to Berkeley from Harvard, eventually becomes a professor there, and one day she gets a phone call from another woman who's interested in RNA, Jillian Banfield, another professor at Berkeley, one who's been studying bacteria that live in really weird places, like the runoffs of Copper Springs or Yellowstone or Kamchatka, Russia, with its high salt and hot water. And these are weird bacteria, and she's studying the RNA of it. It's sort of a lesson, by the way, that Jennifer learned back in Hawaii, which is she played soccer. And because her school was so small, the boys and girls played on the same team. And she realized that the boys on the team always ran to where the ball was. I mean, you've seen fifth grade soccer games like that. The ball goes there and everybody crowds, and nobody's playing their position. And she said, I like to see the whole field. I like to play my position. I like to be where the ball's going to go, not where the ball is. And around the year 2000, there were a lot of alpha males running to the ball. What was it? It was the Human Genome Project. It was DNA. It was sequencing the entire DNA of the human species, of a human. And those of you who remember it, very famous, the great Francis Collins, James Watson was on it, Eric Lander, Craig Ventnor, all of whom, as you probably know if you know of them, are quite alpha males. And there are very few, if any, women involved in the Human Genome Project doing DNA. So most of the women of that time, who were sort of ahead of their field, become interested in RNA instead. They know that RNA might be the secret that not only unlocks how life began, but how we form proteins, whether it be a spike protein in a coronavirus or a way to allow immunotherapy in cancer. So Jillian Banfield, who had never met Jennifer Doudna, even though they're both at Berkeley, they meet at the Free Speech Movement Cafe near Sproul Library, and Jillian Banfield has a pile of papers on this weird thing that people have discovered in bacteria, especially bacteria from extreme places, which is the bacteria have repeated sequences in their DNA. And they're clustered, repeated, regularly interspaced sequences. And nobody knows why. I mean, a bacteria is not going to waste a whole lot of time repeating its genetic code or having these things where it repeats, but there's mysterious coding in between that nobody can figure it out. Francisco Mojica was also studying it. He's the one who came up with the name CRISPR. He worked in, still does, in Alchiante, Spain, and he was looking at bacteria from the very hot waters and springs on the Mediterranean in Alchiante. And one day, they were calling these SPRDs, or repeated, and one day he's driving back and forth, and he decides we need a name for it. And he's the one who takes the idea of calling it CRISPR, for the clustered, repeated, regularly interspaced. Forget what it stands for. He just reverse engineered it so he could have a fun name. His wife says, that's ridiculous. It sounds like a puppy dog. He says, that's perfect. We don't want to make it sound intimidating. And so he does it. One of the interesting things, too, is those of you who are in cancer research, those of you who help fund or promote cancer research, those of you who are in private philanthropies, you know the role of both government, academics, and even industry. Two people from industry suddenly get into this. That's Rodolphe Barangu and Philippe Horvath. They're working in food science. They work for Danisco, a company that makes yogurt, cheese starters, and whatever. Rodolphe Barangu, the guy on your left, is from Paris, and he'd always been interested in food. So he decides to go to the University of North Carolina to do food science. I loved meeting him because I'd never met anybody who loved food and decided to move from Paris to Chapel Hill, North Carolina. But he did. And he and Rodolphe Barangu are both working in the same company, working sort of calling and collaborating virtually every day, because the biggest problem Danisco or yogurt makers or cheese starter makers have is that they use bacteria as part of a culture to make the to make the yogurt, to make the cheese starter. And the bacteria each year get threatened and killed en masse sometimes by virus attacks. Now you think we have problems with viruses. The biggest battle on this planet in all of the history of life is the battle between bacteria and viruses. Billions and billions per minute of bacteria are killed, or sometimes the bacteria kills the virus. And the cool thing that these two scientists had was they had a record of every bacteria culture going back 20 or 30 years, the DNA sequencing, because Danisco kept it, and what happened and how those things changed. And they noticed that the clustered repeated sequences came along every time there was a virus attack. The bacteria who survived the virus attack put a snapshot, a mugshot, you could call it, of that bacteria's, an essential little part of its DNA, into these clustered repeated sequences. So if the virus ever attacked again, it would be able to use an enzyme to chop the virus. And that's all CRISPR is. It's a pretty simple method in which bacteria take an enzyme, attach it to a guide RNA that says, if you ever see this, go there and cut it. And that's how these bacteria survive virus attacks. The good thing about research science is sometimes it's just driven by curiosity. Originally, Gillian Banfield and even Francisco Mojica, they weren't looking, they didn't say, hey, someday we'll have a coronavirus attack and we'll have immunotherapy in cancer. We're going to need to use this. They were just doing it out of pure curiosity. Why do these bacteria have these systems that they called CRISPR? But the great thing about science and why CAGLA and advocates like you are so important is it's not just saying, okay, let's go in the lab and do this. You have to make the basic scientific discoveries that form the seed corn for then what will become the tools that you don't even know you're going to find when you look for the basic discoveries. You don't know, if you're working at Bell Labs, that looking at how electrons dance on the surface of semiconducting materials, you're doing that out of pure curiosity. But at some point, when you make discoveries about it, you say, I get it. We can make a transistor. We can change the world by figuring out how to do semiconductors. Likewise, these people are doing CRISPR not knowing where it's going to lead, but of course, it ends up leading to many important places for health and especially for cancer. Once again, another great woman enters the tale. I'm sorry for you men in this room. This was not meant to be this way, but as I was writing the book, I realized this is an important thing, a theme. This is Emmanuelle Charpentier from Paris. She was then at the University of Vienna. And at conferences. Why are you doing this conference here? Because you're going to meet people. You're going to exchange contact information. You're going to say, what are you working on? What's new? What's interesting? So they're at a conference in Puerto Rico, never met each other, walking on the cobblestone streets. And Emmanuelle Charpentier says, oh yeah, I'm working on CRISPR. And Doudna says, wow, yeah, Gillian Banfield just introduced me to that. Maybe if we use this idea of a guide that will cut DNA in bacteria, we can figure out how to make a tool out of it. And so along with their graduate students, Emmanuelle Charpentier and Jennifer Doudna, and two of their graduate students, Jennifer and her graduate student, Martin Yinnick, are in Berkeley, and Emmanuelle and Chelinsky, her graduate student, are in Vienna. They work for about a year on figuring out exactly how to use CRISPR as a tool, not just as a miracle of nature. This is their paper. You can see their names on it. They always start with the graduate students, as you know, on the names. But that's Martin Yinnick, and then it ends with Emmanuel and Jennifer. And don't worry about the title, although most of you will understand it because you're science geeks in a way. But basically, all you have to do to translate it is, how do you take an RNA guide and use a scissors, that's what endonuclease means, to cut DNA. How bacteria do it to become immune. Or to stop, autoimmunity, other things, it just deals with immunity. And from that paper comes a notion. At the end of the paper, they have a sentence very much like the end of the double helix, in which the paper on the double helix, Watson and Crick say, it has not escaped our notice that the structure of DNA can be a way that genetic information is passed on. They say it's not escaped our notice that we could take this tool and edit our DNA. We can edit human genes. This is what we've come up with. Now, they've come up with the idea that this could do it. They haven't yet proven it could work. And so this paper starts a race. And this is just 11, 12 years ago. Starts a race for people to say, all right, we've got to make this tool. Because this is a scientific discovery that will eventually win the Nobel Prize. But if you want to win a patent, you have to show it in practice. You have to show it working. So there's a great race. Jennifer and her team, Feng Zhang at MIT, and George Church at Harvard, all three racing against each other. And in January of 2019, each of them accomplish it, with Feng Zhang technically winning by about a week or two, and also doing an expedited patent application from the Broad at MIT with Eric Lander, and winning the patent. Lawyers in the room will know what's happened. This is still a patent battle that's still going on. I sometimes think we overdo the patents and the battles. At some point, when the microchip is invented, both by Texas Instruments and by Bob Noyce at Intel, eventually Noyce calls Kilby at Texas Instruments and says, after about a 12-year patent battle, let's quit fighting over divvying up the proceeds until we finish robbing the stagecoach, and they get rid of the lawyers and settle their case. I think it's about a year or two from that happening here, where all of them will settle. But even without the settlement of the patent cases being used extensively, this is the first person ever to be totally cured of a genetic disease using gene editing. Victoria Gray of the Delta country of Mississippi, I think Clarksdale, goes to a hospital in Memphis, and she has sickle cell. And they take the stem cells that make her blood cells. They, as you know, sickle cell is just one letter out of how many billion? I can't remember. A lot, yeah, of the 3 billion letters of our day. One letter, one A becomes a T by mistake. You get crumpled blood cells that don't carry enough oxygen. They edit it, and she becomes the first patient to be totally cured. By the way, I've been following her ever since the book has been 2 or 3, 4 years now. Just last week, she was in London giving a lecture. So this wonderful woman from Clarksdale is now sort of an international celebrity for the first person to be cured by gene editing. This is David Suarez. I talked to a lot of people who are bioethicists, because you have to wonder, what is the ethics from using some of these? I'm sorry, I'm just looking at the time here, but yeah, well, yeah. So the ethics of using it. Now, he's got sickle cell. He loves playing basketball. He's a great kid. But his problem is when he plays basketball, he sometimes crumples up in the middle of the court because his blood cells aren't giving him enough oxygen. He goes into a sickle cell attack. And they explained to him, not only will CRISPR be able to fix your sickle cell, but they can do it in a way that affects your reproductive cells, your sperm or your egg, so that it'll be edited out of your family, because it's a hereditary disease. Your children will not have it. None of your descendants will have it. We can edit your family, we can edit in an inheritable way your DNA. And he says, great. But then a few weeks later, he's talked to, and he says, well, maybe it should be up to my children to decide if they wanted it edited out. And they say, why? Why would you want? He says, well, sickle cell was bad. It made me crumple up at times. It caused me great pain. But it also taught me persistence. It made me who I am. It's part of who I am. It taught me to get up off the floor. It taught me empathy for other people. I mean, we're pretty happy we cured polio, but had polio not existed, Franklin Roosevelt would have spent his life as a Upper East Side playboy and never become president. No, it's true. So sometimes we have to figure out when do we use these things? So I finally called him back, and I said, why would you think? He said, well, I've changed my mind again. I do want to make it to my kids. I don't want them to have the pain. And I said, well, what made you change? He said, well, I'll try to teach them empathy. I'll try to teach them persistence. Now, I say this not because he comes to the right answer, but because he does the right thing, which he goes back and forth. He wrestles with the problem, and that's what we're going to have to do, is continue to wrestle with this problem. Why? Well, when Jennifer Doudna first published her paper, she had a nightmare. And the nightmare was that somebody wanted to see her. Somebody wanted to go inside of her to come in a room and wanted to meet her. And when she gets to the room, it's Hitler. Looks up, it's Adolf Hitler. And she wakes up in a panic because the Hitler character says, I want to learn about this gene editing technology you have. I want to create the master race. I want to use it for eugenics. And so she starts convening scientists from around the world, still working on it, to answer the ethical questions that we're going to face in this life sciences revolution, which is, how much are we going to edit our children? There are things we can do. Curing baldness, that's really not going to be that big of a deal. Low risk of Alzheimer's, perfect pitch, better vision, higher IQ. Yeah, that's not going to be the hardest of all. If you can cure sickle cells so that the cells aren't deprived of oxygen, you can also go further and create children with blood cells that carry extra oxygen. So they will become the great sprinters and athletes. As Putin says, you can create them so they don't feel as much pain, so they'll be great Russian soldiers. There's much you can do, and you can see where we're getting on tricky territory. One of the territories is, you can make your kid taller, make them carry more oxygen, you make them a great athlete. And what if everybody, I'm not as worried about state-sponsored eugenics like the Nazis tried to do, but what if an ordinary parent into a fertility clinic, still has to be done by IVF, but you do it in a fertility clinic, and you edit the early stage embryo, and you say, here's what I want. What would they do? What would you do? You get into a very closed room and nobody's going to know your answers. You just get to go to the genetic supermarket and say, do you want them taller? Do you want hair color? Sexual orientation? Do you want to choose that? Do you want to choose higher IQ? And perhaps we'll start editing out deafness, certainly sickle cell, maybe shortness, maybe, many other things, hair color. And we will start engineering our species in a way that does with the free market what state-sponsored eugenics tried to do by forcing this type of thing. And one problem, of course, is this ain't going to be free. You can't get things at the genetic supermarket for free. The process is going to cost money. So what happens if the rich get to buy better genes for their kids? We privileged people already have SAT tutors probably for our kids, or at least advantages, get to go to soccer camps and stuff. What if anybody who could afford it could make their kids taller and smarter, whatever? Do you get to the Aldous Huxley Brave New World, where you have a genetically enhanced subspecies of privileged people and the alphas, and then have the genetically unenhanced subspecies? You end up the problem of editing humanity, and indeed having eugenics come back. I tried to learn the technique. It's not that hard, somewhat frighteningly. I spent 2 days in Jennifer's lab and was able to edit a human kidney cell so that it glowed in the dark. Just put in a phosphor gene. Don't worry, we flushed it down the sink with a lot of chlorine, so it's not part of the human race. But if I can do it, it's not going to be that hard in 10, 15 years for this to be done. In fact, the first person to create designer babies already did it 3 years ago. He Zhuangqi from China. There he is taking a selfie with Jennifer. Jennifer didn't quite know who he was, but that's the auditorium at Cold Spring Harbor Labs, where they have annual conferences. Some of you have been there. Great place. Jim Watson was in charge of it until they ousted him for the things we won't talk about. But he does a selfie with her and goes back to China and edits the embryos of what would become 2 baby girls, and edits them so that they no longer have the receptor for the virus HIV that causes AIDS, because he was in a place where AIDS was running rampant, and it's pretty simple to just take out that receptor. Well, all hell breaks loose. I mean, there's all sorts of international conferences. Even China puts him under house arrest, takes away his license, because the Chinese and the US are on the same page, along with many other countries, because Jennifer and a lot of people have created this notion. Let's not do inherited gene editing before we figure out the rules of the road. However, when COVID comes along, I start thinking, and even Jennifer a little bit, which is, remind me again why we wouldn't edit the human race to take out receptors for certain viruses. You don't want to have unintended consequences. There's a lot of unintended consequences when you start messing with genetic material. You take out the receptor for HIV, and it makes you more susceptible to malaria and West Nile. But let us suppose you can figure out the unintended consequences. Would we want to edit our species to be resistant to viruses? Well, every other organism uses every tool in its toolbox to survive. That's how CRISPR came along. Bacteria. Now, bacteria aren't much smarter than we are. If they do it, why shouldn't we be doing it? And then, how far do you really go? This is a company that Jennifer starts to do it in a way to detect viruses right before COVID hits. So it becomes, by the way, the company you should have invested in, but it can immediately detect, just like bacteria can, if there's a coronavirus coming. And soon, it'll be able to just cut it the way a bacteria would, which is the therapeutics that we really need for viruses. Because as much as we love the vaccines, as you know, the vaccines are kind of messy. If we could just say, anytime anybody gets COVID, they just have an RNA therapeutics, which will kill the COVID virus in your system. Be a lot simpler. The good thing for me is I was trying to finish the book in 2020, and I think it's October when it happens. I was here in New Orleans, and usually they don't give the Nobel Prize to something that's only 8, 10 years old. In fact, in 2020, the physics prize was won by Sir Roger Penrose for a discovery he made 50 years earlier. So I'm thinking, it's not likely, but boy, it's going to be a great last chapter if it happens. 4 a.m., I think it was, in New Orleans, I'm getting up, listening to on the internet, the live stream, And finally, the head of the Swedish Academy says, this year's prize is about rewriting the code of life. And I go, yes! And then I have to wait, because they usually give it to 3 people. And of course, they give it to, he says, Emmanuel Charpentier. They're going alphabetically. Jennifer Doudna. And I'm waiting to see, because it's almost always a third. And I'm waiting to see if Feng Zhang, the guy who at MIT. And they don't. I don't know why. I can't crack the code of the Swedish Academy. But it's just given to the 2 of them, which at least ends the book well. That's Jennifer in her kitchen with her husband Jamie, and and her son Andy, in her kitchen that morning when she gets the phone call. There are some of you wondering, how do we have a picture of this moment? If you've ever been to Berkeley, Berkeley loves Nobel Prizes. It gets a lot of them. If you win a Nobel Prize, the big thing, other than the $1 million or so, is you get a parking place on campus that they give you. So on the night that the Nobel Prize is being, and this is, 4 a.m. there, so it's 2 a.m. When it's being announced, the Berkeley News Office positions photographers right up by the houses of every person they think might win the prize. They have like 10 photographers in various places. And this year, there's a photographer on the porch of Jennifer Doudna's house when she gets the phone call. That year, March 2020, is when it all hits. I lived on we have a place on Royal Street, that's our balcony. And I took pictures of people from Mardi Gras. And people were dressed up as the coronavirus. We didn't yet know, I think it was late February. We didn't yet know it was going to be a real problem. And so it was kind of a joke. You wore the corona bottle and the mask and stuff. It was a whole lot of fun until a few weeks later when we locked down. But sitting on that balcony later, as I was writing the book, I thought, okay, what are the implications? Let's start a discussion about this, because this will transform the life sciences for good, but it will also transform humanity for good or for bad, depending on the conversation that we have to have over the next 20 years. We will not be editing children the way I talked about, even though He Zhongqi did it once. We're not really going to have this for 10 or 20 years. But during that period, we have to make sure it doesn't get politicized, that it doesn't become a left, right, or Democratic, Republican, whatever issue, that we figure out what are the rules of the road, not only for us, but around the world, going to be. That weekend that I was writing the end of the book, on that balcony, was, how many of y'all from New Orleans? Oh, wow, okay. So you know this. This is one of those typical New Orleans weekends. Leah Chase, the Grand Creole chef, had just died. So there was a second line for Leah Chase. So had Dr. John, the great funk musician. So there was another parade celebrating Dr. John. It was the Gay Pride weekend. So there's a Gay Pride parade with a whole lot of block parties right on Royal Street. And people from Gallaudet University were having a conference there, meaning for the deaf. It was also the Creole Tomato Festival, celebrating non-GMO tomatoes in the French market. And to top it all off, and when I talk about this in other places, they think I am making this up, but you're from New Orleans, so you know this. There's the naked bicycle race, which many of you have heard of, which is designed to promote traffic safety. Now go figure out why naked people on bicycles are going to promote traffic safety. All of that is happening, but I'm seeing people on Royal Street, sitting there on a balcony with our wife, who are gay and straight, trans, tall, short, skinny, fat, black, white, cafe au lait, Creole, Asian, deaf and hearing enabled, all sorts of things. And I say, this is what I love about New Orleans, the diversity of the place. And then I think, this is what I love about the human species, the diversity of the thing. And then I think, This is what biology loves about the human species, that its diversity is its strength. This is how we will survive as a species. And then I think about gene editing and the role it could play in reducing that diversity. And so that's why I wrote this book, and I hope it leads to greater conversations that y'all will be a part of. Thank y'all very much.